Welcome back, everybody, for another deep dive. This time, we're taking a look at neural networks.
Yeah, these things are pretty amazing.
I know, right? We've got some pretty intense source material for this one.
Oh, yeah. Definitely a bit technical.
But as always, we'll break it all down, make sure it all makes sense. So by the end, you'll have a really good understanding of how these things work, like what even is a neural network.
Think of it this way. It's kind of like getting a peek under the hood of AI.
Ooh.
We're going to be exploring, what they are, how they learn, and why they're becoming so important these days.
Well, the source material we're looking at starts by comparing a neural network to a simple mathematical function. It's like a recipe with ingredients like inputs and weights, a bias term, and then you get a specific output.
Right, and what I find fascinating is how this seemingly simple equation gets really powerful when you stack multiple layers of these
neurons.
Yeah, neurons.
Yeah.
On top of each other. Yeah, that's what's so cool about these things. It's like this simple idea, but then you scale it up and boom, suddenly it can model all these complex relationships.
That's the key to their ability to, handle complexity. Each layer builds on the processing of the one before it. It's like refining the data as it flows through the network.
So is it more like a multi-step recipe?
Yeah, you could say that.
Where each step adds complexity to the final dish.
I like that analogy. Mm-hmm. And each neuron in those layers has this thing called an activation function.
Okay.
Which we'll get into later.
Yeah.
But it's basically essential for making sure the network can capture the nuances of real-world data.
Okay, got it. Now, I'm a visual learner, so I always need a picture in my head.
Sure.
Luckily, the source material has this diagram that shows the structure of a basic neural network.
Oh, nice.
You've got the input layer where the data comes in. Then there's a hidden layer in the middle where the processing happens.
Right.
And then finally, you've got the output layer where you get your results.
Think of the connections between those nodes, those little circles, in each layer as weights.
Okay.
These weights basically control how much influence each input has on the final output. And the cool part is, the network actually learns and adjusts those weights over time.
Oh, so it's always fine-tuning itself.
Exactly. Like it's constantly learning, getting better.
To become more accurate.
Yeah. But how does it know which way to adjust those weights?
Yeah, that's what I was wondering.
Well, that's where the idea of gradient descent comes in.
Gradient descent, huh?
You can think of it like a hiker trying to find the lowest point in a valley.
Okay.
They're going to take small steps downhill, right? Okay. Always following the steepest path.
Makes sense.
So in a neural network, the valley represents this error function, and the steps are adjustments to the weights. The network is basically trying to find the set of weights that minimizes those errors.
So it's trying to get to the bottom of the error valley.
Precise.
But with all those connections and weights, how does it figure out which way to go for each step? Like, how does it even know?
That's where the magic of backpropagation comes in. This algorithm calculates those gradients, those directions, for how to adjust each weight across all the layers. Think of it like a map for our hiker.
Oh, so backpropagation is like the hiker's map, showing the best route down.
Exactly.
And then each step the hiker takes is like a tiny tweak to one of those weights, guided by this gradient descent.
You got it. Now, here's a fun fact the source material brings up. You might think it makes sense to initialize all the weights at 0 at the beginning.
Yeah, I guess that would make sense, like starting from neutral.
Well, it turns out that if you do that, all the neurons in a layer basically end up doing the same calculation.
Oh, so you need some variety.
Yeah. It's like having a choir where everyone sings the same note. It's not very interesting.
That's a good point. So you need to mix it up a bit.
Exactly. So by initializing the weights randomly, you introduce that much-needed diversity.
It's like giving each singer in the choir a different part.
Yes. That random initialization breaks the symmetry and allows each neuron to specialize. It's like they each have their own unique voice in the network.
Huh. That's fascinating. So it's not just about the connections, but also about how you start them off.
Right. It's all about giving the network the tools it needs to learn and adapt effectively.
Now, we've mentioned these activation functions a few times. What exactly are those, and why are they so important in this whole process?
They're basically like adding another layer of complexity to each neuron's processing.
Okay.
They're what introduce the nonlinearity that we keep talking about. Without them, the neural network would essentially just be a simple linear model, even with all those layers.
And that's a problem because...
Well, imagine trying to draw a portrait, but you're only allowed to use straight lines. You'd have a hard time capturing the curves and contours of a face, wouldn't you?
Yeah, I guess so. You need those curves to make it look real.
Exactly. And that's what these activation functions do. They help the network capture those subtle curves and patterns in the data.
So they allow it to model those complex relationships.
Exactly. They make it possible for the network to learn the nuances of the real world.
I see. Now, the source material mentions a few specific types of activation functions, like there's sigmoid, tan, ReCLU, and leaky ReLU. Do they explain how each one works?
They do. There's even this handy table that compares their pros and cons. It's like each one has its own unique way of shaping the output of a neuron, making it better suited for certain tasks.
Oh, so it's like choosing the right tool for the job.
Exactly. But I think we'll save that deeper dive into activation functions for the next part of our conversation.
Okay, sounds good. So we've talked about how a neural network is structured and how it learns, but what about its ability to process massive amounts of data? Like, I know these things are used with huge data sets.
Oh, yeah. And that's where this concept of vectorization comes in.
Vectorization.
Instead of processing data points one by one, neural networks can handle multiple examples at the same time using matrices.
So instead of baking one cake at a time, we're baking a whole batch at once.
Perfect analogy. And that makes the calculations way more efficient. It's super important when you're dealing with huge amounts of data.
That's really impressive. I mean, it's incredible how all these mathematical models can learn and adapt like this.
It's pretty remarkable how far this field has come.
Yeah. And in the next part, we'll be diving even deeper into those activation functions and see how these neural networks are actually being used in the real world.
Definitely. There's some really cool applications out there.
Absolutely. But for now, let's take a short break. Be right back. So we've covered like the structure of neural networks, right? And how they learn from data using gradient descent and back propagation. We also talked about those activation functions.
Right, how those are important for introducing nonlinearity.
Yeah. And that gives them the flexibility to model all those complex relationships.
Yeah.
Now I'm really curious to learn more about those activation functions. You mentioned that the source material goes into detail about how each one works.
Yeah, definitely. It highlights a few key ones, like sigmoid, tan, ELU, and leaky ReLU.
Okay.
And it even has a table comparing their strengths and weaknesses.
Oh, cool. I'm looking at that table now.
Yeah.
And it seems like each one has its own unique shape and characteristics.
Yeah.
So what makes one activation function better for certain tasks than another?
That's a great question. Let's start with sigmoid. That one's been around for a while, and it's known for squashing the output of a neuron into a range between 0 and 1.
So it's like compressing the output.
Yeah, exactly. So particularly helpful in tasks like image classification.
Okay.
Let's say you're training a neural network to recognize different breeds of dogs.
Okay.
The sigmoid function could be used to output the probability that a given image contains a golden retriever, for example.
So the output would be something like 80% chance this is a golden retriever.
Exactly. And that kind of output is really useful in a lot of real-world situations.
Cool. What about the other activation functions?
Sure. So tan, that's short for hyperbolic tangent.
Okay.
It's similar to sigmoid in that it also squashes the output, but its range is between -1 and 1.
Okay.
So this is helpful in some cases where you need both positive and negative outputs.
Interesting. What about ReLU, the rectified linear unit? The table says it's pretty popular.
Yeah, ReLU is a favorite because it's computationally efficient.
Okay.
It's really simple. It basically just sets any negative input to 0 and keeps positive values the same.
Oh, so it's like a switch that just turns off any negative signal?
Yeah, exactly. That simplicity makes it faster to compute, which is a big plus when you're training those large neural networks.
That makes sense. And then there's leaky ReLU. Is that just like a variation of ReLU?
Exactly. Leaky ReLU is designed to fix a problem with standard ReLU.
Oh, what's the problem?
So with ReLU, if a neuron gets stuck, always outputting 0, it basically becomes inactive, and stops learning.
Ah, so it's like a singer in our choir who's suddenly gone silent.
Yeah. Leaky ReLU fixes this by introducing a small non-zero slope for negative values.
Oh, so it's like giving those silent singers a little nudge to keep them going.
Precisely.
I like that.
So the main takeaway here is that each activation function has its own little quirks, which makes it better for certain tasks or, certain types of networks.
It's really cool how all these different parts work together to make such a powerful tool.
Yeah, it's pretty amazing.
Now, earlier you mentioned how neural networks are being used in things like image recognition and medical diagnosis. Can you give us some specific examples of how they're being used in the real world? Like, what can these things actually do?
Of course. Let's start with image recognition. Neural networks are powering all sorts of things, from facial recognition systems to self-driving cars.
Wow.
They can analyze images and identify, objects, scenes, even emotions with really good accuracy.
So when my phone unlocks with my face, that's probably a neural network working, right?
Most likely, yeah. And in self-driving cars, neural networks process data from cameras and sensors,
Right.
so the car can navigate and avoid obstacles.
That's incredible. What about in healthcare?
Well, they're showing a lot of potential in helping doctors diagnose various conditions.
Okay.
For example, researchers have developed networks that can analyze medical images like X-rays and MRIs
Okay.
to detect signs of cancer or other diseases.
Wow. So they're like specialists who can spot these tiny details.
Yeah. And they can process huge amounts of data, which might help with, earlier and more accurate diagnoses.
That's amazing.
But it's important to remember that these networks are still tools to assist doctors, not replace them.
Right. Of course.
Yeah.
They're like giving extra insights.
Exactly. And beyond these examples, neural networks are being used everywhere, from natural language processing to financial forecasting to even drug discovery.
Wow. It seems like the possibilities are endless.
And that's what's so exciting about this field. Researchers are always developing new architectures and training techniques, so who knows what incredible applications we'll see in the future.
It's kind of mind-boggling. This deep dive has really helped me understand not just like the technical stuff about neural networks, but also their impact on the world.
Yeah, I agree. It's amazing to see how far we've come.
Before we wrap up, is there anything else in the source material that you think is important to know about neural networks? Like any key takeaways?
There's one more interesting point I think we should mention.
Okay, what's that?
The source material talks about overfitting, which is something you need to watch out for when you're training these networks.
Overfitting.
Yeah. Imagine you're teaching a student for an exam, and you only give them practice questions from one textbook.
Okay.
I bet they'll ace the exam if the questions are from that same textbook.
Right.
But they might struggle if they see new material.
Yeah, they've only memorized the answers from that one book.
Exactly. They've overfit to the examples they were given. They haven't really learned the concepts.
So how does this relate to neural networks?
If a network is trained for too long on the same data,
Okay.
it can start to just memorize the training examples
Oh.
instead of learning the general patterns.
I see. So it becomes like that student who's only good at answering questions from one textbook.
Exactly. And when that happens, the network will do really well on the training data, but not so well on new data that it hasn't seen before.
So how do you stop a neural network from overfitting?
There are a few techniques, and the source material goes into detail about some of them.
Okay.
One common approach is to split the data into training and validation sets.
So you train it on one set and then test it on a completely separate set.
Yeah. That helps make sure that the network is learning general patterns, not just memorizing examples.
Oh, that's smart.
There are other techniques, too, like regularization.
Okay.
That adds a penalty to the complexity of the network, so it doesn't get too specialized to the training data.
So it's like encouraging the student to learn the core concepts instead of memorizing every single detail.
A great analogy. And that brings us to an important point about developing and training neural networks.
Yeah.
It's not just about, throwing data at a model and hoping for the best.
Right.
It takes careful planning, thoughtful experimentation and a good understanding of how these things work.
Yeah, it sounds like a mix of art and science.
Definitely. It
So-
requires both technical skills and intuition.
This deep dive has been really eye-opening. I'm starting to see how powerful these neural networks are, but also how important it is to use them responsibly.
That's a great point. As neural networks become more sophisticated and more integrated into our lives,
Yeah.
we need to have serious conversations about the ethical implications.
It's a good reminder that even the most advanced technology still reflects human choices.
Well said.